Hey guys, today we'll continue in our series where we go through the courses in FPGA Academy, and today we'll look at Lab 5, timers and real-time clocks. Last time we finished Lab 4, counters, so if you haven't seen it you can watch it on my YouTube channel, and let's look at Lab 5. But today we will try to finish part 1, 2 and 3, and in the last part, part 3, we will try to implement real-time clock. So that's a clock that counts minutes, seconds and hundredths of a second, and it will display them on the 7-segment displays. But before we look at part 3, let's finish part 1 and 2. So in part 1, we will try to create modulo-k counter. So that's a counter that only counts up to k-1 and then it resets to 0. So for example, if we have counter that is 3-bit, so it's a 3-bit counter, it can count from 0 to 7, but if we set k to 5, it will count from 0 to 4, and then it will reset to 0. This counter will also have value called rollover, and this will be output value of the counter, and it will be set to 1 in the clock cycle when the counter gets resetted. Otherwise it will be 0. So that's all for the description. We will also do functional simulation, and then we will try to run this code on our board. So let's start. Here I have a counter, very similar to what we have done in the previous part, and we will create modulo counter out of this counter. So let's create a new file, and let's call this counter modulo, and let's save it. And here you have generic. This sets how many bits the counter has. So by default, this will have, let's say 5. And then we set k, that will be our modulo. And it's gonna be also natural, and let's set it to 20. So this will be 5-bit counter, which gets to be resetted at 20. Then we have clock, enable, and reset n as inputs, and q as output. So here if enable is equal to 1, we increment the counter. So I'll add one more if here. So if count equals to k, then we do something else if enable is equal to 1. So if count is equal to k, we will reset the counter as we have done here. So count will be resetted. And also we need one more output here called rollover. It will be out and std logic. And here we will set it to 1. Else we set it to 0. And here else here we set it to 0 as well. So this should be enough for our modulo counter. If the counter is equal to k-1 actually, k-1, it will get resetted. Otherwise, it will just keep incrementing. Let's set this as top level entity. And now we will do functional simulation to see if our design is correct. I will create university program YWF, and here we insert our nodes. So by doing this, we insert our clock, enable, reset, and rollover. These are our inputs and outputs from our counter modulo. We will set this to 1 as well as this to 1. So reset and enable will be 1. Clock, first we set end time. We will set this to, so the simulation will run for 100 nanoseconds, and the clock period will be 4 nanoseconds. I have set the clock to be 4 nanoseconds, and we can run the simulation now. And let's set this to be unsigned decimal. So we can see our counter counts from 0 to 19, and then it resets to 0. And when it resets, it also sets rollover, this value, also set to 1 for 1 clock cycle. So this seems to be correct, this behavior. And we can continue. And let's create in part 1. Let's import our entity counter modulo. Here we import it as a component. And here we create one instance. It will be called counter20. It will be instance of this and port map. And clock will be key 1. Then enable will be, let's set it to 1 for now. Then reset will be key 0. And rollover will be shown on LEDR9, so the last LEDR. And since we have n equal to 5, then n minus 1 will be 4, so this output will be 4 down to 0. We will show the output on LEDR4 down to 0. Let's set this as top-level entity and compile. Compilation is done, so we can test it on our board. So let's look at the board. So you can see that, I'll reset it. So we can see that all of the counts, or all of the LEDs are set to 0, which means the counter has value 0. And if I press key 1, which is our clock, it will, so first LED is turned on. So that's value 1, then value 2, value 3, and so on. This is the binary value of the counter. So you can see it goes all the way until 19. And then our rollover is set to 1. So our counter got reset and rollover is set to 1. So this is the correct behavior. I can also set some value, and then when I press reset, it will reset the counter to 0. So we can see it works correctly. And we can continue. So let's continue. We will look at part 2, and let's read the description. Using your modulo counter from part 1 as a sub-circuit, so we will be using the counter that we have just made. Implement a 3-digit BCD counter. So we will implement counter that will count from 0 to 999. BCD number means number between 0 and 9. And we will display them on 7-segment displays 0 to 9. And also switch or key 0 will work as reset. And we will be using 50 MHz clock, and it will increment the number once every second. So every second the counter will increment by 1, and it will count from 0 to 999, then it will reset to 0. And we can look at this diagram, which displays what we will just try to implement. First, we have our clock 50 MHz here, and our first counter that will count from 0 to 50 million, which is which will set the rollover to be 1 once every second. So this will count from 0 to 50 million, because 50 MHz clock means that we have 50 million cycles per second. So it will increment this 50 million times, then it will reach the value 50 million and it will get reset. And this will last for 1 second. And then this will enable the next counter, which counts from 0 to 9. And that will count from 0 to 9 once every second. Then when this reaches 9, it will set enable for the next one. So this will get reset to 0, and this will set or increment by 1. So if this is 0 and this is 9, on the next enable for this one, this will be reset to 0 and this will be set to 1. And then we will also display these on the 7-segment displays. And these displays, or these counters, will be 4-bit counters, and the k will be set to 10, because 2 to the power of 4 is 16, and that's the first power of 2 that is bigger than 10. This one will be 26-bit counter, and it will count to 50 million, and 26, because 2 to the power of 26 is the first power of 2 that is higher than 50 million. We have already done this in the previous video, so you can watch it if you don't fully understand. So let's try to implement this now. I will create part 2 for this, and I will copy part 1. I'll call this part 2, and we will need switch as inputs in std logic vector, and it will be 9 down to 0. Then we also need our clock, 50 megahertz clock, that's gonna be clock 50 in std logic. And then we need our hex 7-segment displays. std logic vector 0 to 6. And we will need 3 of these. And that's all for our ports, input and output. And now we will look at the counters. So first we will create counter 50, and we will also create some signals. We will create signals for these outputs, as well as for these rollover outputs. So we will create 3 rollover signals for these wires, and then 3 outputs for these signals. Actually 4 and 4. So rollover 50, it's gonna be for the first counter, and it's gonna be std logic, and we will create, we can maybe create array. So t or ROT is array 0 to 2 of std logic. I think that's the correct syntax. And then here I will use this. We can also just set this to std logic vector basically. So I will copy this here, but here we can just set this to be std logic vector and 2 down, or 2 to, or 0 to 2. And here this will be qt, and qt will be std logic. It will be the counter of std logic vector 3 down to 0. And we need one more, and this one will be Q50. It's going to be 25 down to 0. So these are the enable or rollover signals of the counters, and these will be the outputs. So the Q50, that's this counter here, will have, since it has 2 to the 26, the binary number will be 25 down to 0, the output, and these will have output 3 down to 0. And we can create our counters. For clock, we will put clock 50 as enable. I will put switch 0, key. So that's reset. That will be key 0. Then output of the rollover will be this signal, and the final output will be Q50. And the first counter, that's this counter here, it will, as enable, it will have rollover from the previous counter. Reset will be the same, and here we set it to rollover 0 and Q0. We will create two more, 1 and 2. This will have rollover from the previous one, and this one too. And here 1, 2, and 1 and 2. And then we have to display them on the 7-segment displays. So I will copy this entity. This is the entity we have created in the second part or third part of this series. And I will copy it here as a component. And let's also save this as part 2. And let's create 3 instances. Segment 0 will be instance of this port map, and it will take as input the output of this counter, and it will display it on hex 0. And 2 more. So that's all for this. And we also have to set our generic. So the generic default value is 5 and 20. So let's set this to 10 and 4. And then we have to just change this generic map. And here it will be 26-bit and it will count to 50 million. Or we can do 25, so it will be half a second. It will increment half a second, so we don't have to wait so long for it to update. So let's start compilation. And we got an error here, and that's because here I have to say type. So we create a new type, and it's called QT, and then we assign it to our signal Q. And we can try to program our board. So you can see there are all zeros, and when I set enable, so that's our switch 0 to 1, it will start counting. And you can see it counts only to 8. And I've tried to see why that is the case, but I haven't really figured out why. If I change the clock here to be key 0 or key 1, one of the keys, it works correctly, but when I put clock here, it just counts to 8 and resets one earlier. And I haven't really figured it out, even though the function simulation is correct. So there has to be some timing issues. But again, if I set the clock to be key, it works. So I'm not really sure about this. But we will fix this by incrementing the counter modulo here. So we will just remove the -1 here, and now it will work correctly. So let's try to compile it now. So compilation is done. Let's program the board. And so it was already counting, so I turned the enable to 0. So when I turn it to 1, you can see it counts from 0 to 9 and then increments the next one. And it will increment also the third one. So now it works correct. Now it's correct. And we can continue with part 3. And in part 3, we will try to implement the real-time clock. And it will display minutes, so 0 to 59, seconds, 0 to 59, and hundredths of a second from 0 to 99. And it will use switches to preset the minute part of the time displayed by the clock when key 1 is pressed. Stop the clock whenever key 0 is being pressed and continue the clock when key 0 is released. Okay, so it's gonna be a little complicated, but it's gonna be not that hard. Let's create a new VHDL file called part 3 and we will copy this code from part 2. But here, so first I will change this to 3 and save this as part 3. We have to add more of these. We will add hex 3, 4, and 5 because we will need all of them. Here, so I will create, we need 3 more, so that means 5 here and 5 here too. And we will create 3 more counters. So counter, and let's call it, so counter 0 and 1, then counter seconds 0 and 1, and finally minutes 0 and 1. So some of these will only count to 5. So I will add generic map. It will be, so these two will count to 9. This one is also 9. This one will be 5. And this one will be 5 too. And 5, that means we need 3-bit counter and change the value at 6. Here also 3 and 6. Or we can just change it to, we can leave it at 4. So our output will be also 3 down to 0. So let's keep it at 4. But we will have to change these. So keys will be the same, but I will indent all of these. So clock will be same. This will be 0, 1, 2, 3, 4. And key will be same. This will be 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5. So that's for our counters. And we have to create 3 more of these. 5, hex 4, and 5. And we will change this to 50 million. So we will divide it by 100 to increment this every 100th of a second. And now we can try to run this on our board. And this should work as a clock. Compilation is done, so we can try to run it. And let's look at the board. So you can see all zeros now. And when I enable the counter, the first two 7-segment displays display the 100th of a second. And the third and the second, or the third and the fourth display the seconds, and the last two display the minutes. So you can see it increments, and we will continue and try to finish part 3, and we will try to create a preset. So if switch 0 to 7 to 0 will be set to some value, and when we press key 1, the minutes part will be set to this value. Also, key 0 will be, if it's pressed, it will stop, and when it's pressed again, it will start again the counter. First, I will create a counter modulo with preset. So I will open the counter and I will create a new file that will be called counter modulo preset. Here I will add one more std logic, and that will be preset enable, and then we will add the value of the preset. So preset val in, and it's gonna be a std logic vector with this size. And here, if preset enable equals to 1, then else if, and I will copy this part. So we will set it to preset val, and preset val is std logic, so we have to change it to unsigned. So this is std logic. We have to change this to unsigned, and rollover will be 0. And so when preset enable is equal to 1, we will change the value of the count to this value. Let's copy this to our part 3, and let's import this as component. And then we have to create our stop signal. So we will enable the counter using stop signal. I will create a signal here called stop. It's going to be a std logic. And let's set this value to 0. So I will create a process that will change on key, let's say key 2. Key 2 will change, or will stop and start our counter. So if on the falling edge of key 2, that means when we press key 2, we will change the value of stop. So we will, if it's 1, we will change it to 0 and so on. And here we will also key, if key 1, key 0, I mean, our reset key, if key 0 is equal to 0, and also in our module, in our preset, this has to be 0, because preset will be activated when it's equal to 0. So I'll change this to n, preset enable n. And let's save this as counter preset, counter modulo preset. Then we will set this to be 0. So if reset is pressed, we will stop the clock, and if key 2 is pressed, we will inverse the stop a bit. So if it's running, we will stop it. If it's stopped, we will start it. And let's compile. And we have to change this to counter modulo preset, and add our preset value. So here we will say key 1 and switch 3 down to 0. So if key 1 is pressed, we will change this counter value to value of the switches 3 down to 0. And I'll copy this here. And here it's going to be 7 down to 4. Okay, this seems okay. So let's try to run this. And also here I will change the default values to these values. Compilation is done, so we can try to finally run this. And let's look at it. So you can see all zeros now, and our enable is key 2. So when I press it, or key 3, so when I press key 3, it starts running. So we can see the hundredths of a second here, seconds here, and minutes here. And we can also preset the seconds. We can also stop the counter and start and stop. And we can also preset the minutes. So I will preset it to 59. So 59, that should be like this. And I can preset it. So you can see 59 here. So when we reach 59 on the seconds, then this should reset to 0. So let's see. So 5 more seconds. And we should see the minutes to reset. And that's what happened. So our real-time clock works as expected. So that's all for part 3. And next time we will look at part 4. And in part 4 we will try to implement Morse code in VHDL. We will try to implement this circuit. So if you want to see it, don't forget to subscribe. And I will see you in the next one. Bye.